Okay, here we go today with a typical exam week crowd in the, the lecture hall today. A couple of announcements I've been asked to pass along. We have Delta Omega Chi has their third meeting on Wednesday right after class, and there's a JAMP workshop. I forget what JAMP stands for, but basically it's a program that allows you to get early admission to medical schools if you're qualified. It is a real thing, because I've had one former student that got in recently, so they have a workshop on what that takes that's hosted by Alpha Epsilon Delta, and that will be tomorrow if you're interested in that in this room. All right, so that information is in the notes. As you're all aware, we have an exam this week, so if you have any last minute questions, please come find me. Should have my regular office hour availability 11 to noon, but I'll be around other times besides that if you want to stop by outside of those couple hours, or let me know ahead of time. We can set up an appointment, whatever works for you. So please, anything you have related to the exam, and if you want to see the exam results, typically we release those if you've already taken it. We'll release those after everyone's done on Wednesday evening, so you can see your full results Wednesday. I'd be happy to also answer any questions you have about the results of your exam. So we're going to continue today with Chapter 4. So we started last time introducing the first major topic in Chapter 4, which is VSEPR, the approach that we use to determine the three-dimensional shapes of molecules. Today we're going to talk about one of the consequences of that three-dimensional shape, which is molecular polarity, and then we're going to start discussing how these different shapes are formed via overlap of atomic orbitals to form chemical bonds. All right. So here's a review of what we did last time. We saw that you can basically classify everything into these AXE notations, where X is the number of atoms bonded to the central atom, E is the number of lone pairs, and that then determines a electron group arrangement, which is given by the steric number. There are 5 different electron group arrangements, and then also depending on the number of lone pairs, you have other possibilities for molecular geometries. I think I left one off of here. There should be AX2E3, which is linear. So don't forget about that one. But again, I don't think the approach to take on this is to memorize this whole table. This can be helpful to refer to as you're learning this topic, but really get comfortable with, again, the 5 different electron group arrangements that we have, going down from linear, trigonal planar onto octahedral, and then drawing out those shapes and figuring out where the lone pairs go, and kind of following the approach that we started learning last time. So let's start then with one more example just to close out this section. So this is a somewhat strange one because we haven't seen molecules like this before. Xenon tetrafluoride. Now we talked about noble gases typically not forming compounds or bonds of any type. There are a few exceptions, and xenon does form some compounds with fluorine, and there's some other even more exotic ones out there. So if we have XeF4, remember that when we want to determine the molecular shape, and also then for what we're going to learn later on today, which is called hybridization, for any of that, we need to be able to draw a good Lewis structure, so that was a topic that's going to be covered on this current exam. So if we go to xenon tetrafluoride, we have xenon, which is in group 8, so you are going to use 8 valence electrons from there. It's a noble gas. And then 4 fluorines, all from group 7, so you're going to have 7 each from those. So we count electrons, we get 8 from the xenon. Fluorine, we get 28 more. So this is going to have 36 valence electrons for us to put into the structure to make sure we have a good Lewis structure. As we talked about last time, for stuff we're doing in Chapter 4 with molecular geometry and, as I said later on, bonding hybridization, you don't necessarily need to have the world's most accurate Lewis structure, but you do need to have the correct number of valence electrons, and especially around the central atom, because that's what all this is focused on, you need to have the correct number of bonding and non-bonding electrons. So let's at least get to that point. So for xenon tetrafluoride, we start with the 4 bonds, single bonds to fluorine, and then we complete their octets. And so doing these Lewis structures proficiently and correctly, so both fast and correct, is going to be important for both Exam 1 and Exam 2 especially, where we have to use the Lewis structures a lot. So we get this structure here. That's 4 octets around fluorine, so that's 4 times 8 or 32. We have 4 more that go on the central atom, so 2 pairs on the xenon as well. All right, so that's the structure we get. Now, for determining the three-dimensional geometry or molecular shape, as we call it, by VSEPR, we can really just stop here. We don't have to worry about double bonds or triple bonds. This one won't have any, so Fluorine typically never forms double bonds anyway, and in this form right here, we have no formal charges, so this is as good of a structure as we're going to get for xenon tetrafluoride. But again, you don't have to necessarily even go that deep if you're just trying to determine the shape, because whether they're single bonds or double bonds, we count them the same in this approach. All right, so that gives us this type of geometry, and then this is going to be, if you use the AXE notation, AX4E2. So there are 4 atoms bonded to the xenon, 4 fluorines, 2 pairs of non-bonding electrons, so it's AX4E2. Steric number, which is the sum of those two, 4 plus 2 is 6. And so remember, anytime we have a combination of 6 electron groups, whether it be bonding or non-bonding or some combination of those, you're going to have the octahedral electron group arrangement. So again, this question doesn't ask for all this, but I'm just kind of going through all the different things that we want to consider. Electron group arrangement is octahedral. As we said, that's the geometry where you have a square, and then you have flagpoles going up and above and below the square, with the xenon at the center. And we have 2 lone pairs to arrange. Remember that the lone pairs sort of take preference and want to be as far away from each other as possible. And the way we do that when we have 2 of them, especially in this geometry, is to put them opposite each other like that. And then we get the 4 fluorines arranged around. So we call this, again, it's just a square here that the molecule makes up. So the molecular geometry would be square or square planar. All right, there aren't very many square planar molecules, especially for main group P block elements, but this would be one of them. Square planar AX4E2, 6 total electron groups with the 2 lone pairs go 180 degrees apart, and that leaves a square plane for the atoms to occupy. All right, any questions on that approach? Again, a lot of practice is going to be needed for you to get efficient at this, but that's what we need to do. We need to draw a reasonably good Lewis structure and then count electron groups to figure out which geometry we're talking about. All right, so what we're going to move on to next then is molecular polarity, because one thing that we're now able to predict once we have the 3-dimensional geometry is whether or not the molecule is polar or nonpolar. Now, we've already talked about polar bonds. That would just be, and again, that's another topic covered in Chapter 3 on this first exam. Polar bonds being, again, 2 different atoms bonded to each other with different electronegativity values. So if you have any 2 atoms bonded together that have different electronegativities, the bond will be polar, so that's for an individual bond. So the direction of the polarity is towards the more electronegative atom. And what that means is, again, that the partial negative charge is going to reside on the more electronegative atom. So the one we introduced in class is if you have the HF bond. Fluorine is the most electronegative atom on the periodic table. Hydrogen is significantly less electronegative than that. So you would get a partial positive on hydrogen and a partial negative on fluorine with, again, some amount of imbalance of charge towards the side where the fluorine is. And then we can also draw this as a vector. And in this section, when we start talking about molecular polarity, it is somewhat helpful to think of polarity as a vector. So it's basically an arrow pointing towards the more electronegative atom. And when we start talking about polarity of whole molecules, that sort of treatment will be useful at times. All right, and then we talk about the magnitude of polarity. We can compare bonds and say which one is more polar and less polar. And that depends on the difference in electronegativity. So it doesn't depend on individual electronegativity values, it depends on their difference. Now, mostly in this section, when we talk about polar molecules, we're going to just make sort of the gross classification of is it polar or nonpolar and not try to necessarily rank things like we did for individual bonds, but that might come up sometimes as well. The magnitude of polarity for an individual bond being determined by the difference in electronegativity for the atoms. So if we have this series of bonds where you have carbon bonded to all the halogens, let's say, we know that the halogens get less electronegative as you go down the series from fluorine to chlorine to bromine iodine, moving down the column. And so then this is going to be the most polar here, carbon being less electronegative than fluorine. That's going to be the most polar because there's the biggest difference between the 2 electronegativity values. And then there's a smaller difference for carbon and chlorine, and even smaller difference for carbon and bromine. And then the carbon-iodine bond, and I've told some people this in office hours recently and probably in the homework review as well, it is helpful to remember that the carbon-iodine bond is basically nonpolar. As we said, no 2 atoms have exactly the same electronegativity unless they're the same atom, but carbon and iodine, at least on the imprecise scale that we use, are both the same electronegativity 2.5. So that's basically nonpolar. So again, the magnitude of polarity depends on how different the two electronegativities are. So we learned all that for individual bonds, and now we're going to start talking about how do we predict polarity for an entire molecule that has more than two atoms in it. All right, so the definition of molecular polarity would be it's an uneven distribution of charge over a whole molecule or a large portion of it. All right, so the idea here is that you basically have, two or more atoms. If it's just a diatomic, we already know how to predict polarity for that. That's just based on the electronegativity of the two atoms. If it's a more complicated structure with three or more atoms, you may not have, you're not necessarily going to have the polarity be just localized on each individual atom, but you might have one side of the molecule is more polar, has more electron density than the other side, but it's not as clearly located on individual atoms. We'll see how that works as we go through some examples. But basically it just means that you have an uneven distribution of charge where one part of the molecule is partially negatively charged, one part is partially positive. These are so covalent compounds, so you're not transferring electrons and making ions, but you have that unequal distribution, just like we do in an individual polar bond. Not so important for us, but that you can measure molecular polarity in a unit called dBi, which is based on a charge and a distance. So it's very small for an individual, on the atomic scale, because we're talking about tiny amounts of charge and tiny distances, but it's 3.34 times 10 to the 34th coulomb meters. So C is the unit coulombs, which is the SI unit for charge. So again, we're not going to do any calculations of this, but this is how you measure molecular polarity, or is in units of dBi, which is a combined unit that involves charge and distance, dipoles being a product of charge and distance. All right, so we call this the dipole moment. Which is abbreviated as Greek letter mu. So there are times where, in certain types of areas of physical chemistry where knowing the precise dipole moment of a molecule in units of dBi is useful and helpful. We're not going to go through any of that stuff. We're just going to be able to, in this course, predict whether or not a molecule is polar, and then perhaps in some situations be able to compare polarities amongst a series of molecules. That's really, again, the depth we're going to go is on that more qualitative level. So how do we predict molecular polarity then? The first thing is that they must have polar bonds. So you cannot have a polar molecule if you only have nonpolar bonds. And maybe that sounds obvious, maybe it doesn't, but that means that there are some categories of molecules where you can just basically look at the formula and immediately tell that it's not going to be polar. So if you have a homoatomic molecule, meaning a molecule that only has one type of atom in it, those are going to all be nonpolar. There's actually one exception to this that I'll show you just to make sure that doesn't ever come up and you guys get mad at me for not telling you. But most of these, if you have the elemental molecules, nitrogen, we'll learn later on that phosphorus exists as P4 in its natural state. Sulfur exists as S8. We don't have to know all these now. We're going to come to them later. But a lot of the nonmetal elements exist as di or even larger order polyatomic molecules. So, O2, N2, F2, Cl2, all of those, if it's just the same atom bonded together, it's going to be nonpolar because all the bonds are nonpolar, right? If you have two of the same atom bonded to each other, it's nonpolar. The one exception where you do have the same type of atom, but it's going to be a polar molecule, is ozone. So if you do O3 and you draw the Lewis structure for this, what you end up getting is this sort of picture. And in this, you get two resonance forms. It's a bent geometry. Do the same. So anyway, I just want to make sure that we're aware of this possibility where there's one example that I can think of anyway, where you have one type of atom in the structure. It's all oxygen, but these ones are polar, and that's because you get formal charges here. So you have a negative and a positive formal charge, no matter in both of the resonance forms. And because you have these formal charges, they do indicate that there's uneven distribution of charge, where the central oxygen is always going to be partially positive because it always has a positive formal charge, and these outer oxygens, which flip between having negative and zero formal charges, are partially negative. So this is an example where you do have an uneven distribution, and furthermore, as we'll learn a little bit later, because of the bent geometry, that also enforces this uneven distribution of charge. So this is the one counterexample to this. So O3 is polar, I'll write that here. But all the rest of these, nitrogen, phosphorus, sulfur, you can just assume those are nonpolar if they all have one type of element in them. But more important than the chemical formula of the compound is the geometry, and that's what we're really going to link today. That geometry that we learned on Monday, we're going to talk about how that plays into determining polarity. So just because you have polar bonds, so the presence of polar bonds does not necessarily mean the entire molecule will be polar. All right? So that's an important point to get out right in the open, is that we can't just look at the chemical formula and say, oh, that molecule has polar bonds, it must be polar. It's not that simple. So the presence of polar bonds does not guarantee that a molecule will be polar. So that's where the geometry comes into play. All right, so in most cases, you're going to have to think about the geometry of the molecule and then decide what does that say about its polarity. All right, so let's go through then the different possibilities that we have for polar and nonpolar molecules. So let's give some examples of molecules that have polar bonds but overall are nonpolar, and let's see why that happens. All right, so probably the simplest one for us to visualize, and there's a few different ones we're going to go through here, but basically in these types of molecules, you have individual bond dipoles. It's not that the bonds cease to be polar, but you have all these different bond dipoles, and there's more than one of them because there's more than one bond, and the individual dipoles cancel out to give an overall nonpolar molecule. And this is where thinking of dipoles as vectors is going to be helpful. So you have vectors that have some magnitude and some direction to them, and if those end up completely canceling each other out and adding up to be zero, that means your molecule has no net dipole moment or no polarity. So they cancel out and they give a molecule that is overall nonpolar. Now the one case of this where I think it's very easy for us to visualize is in the molecule carbon dioxide. So if we were to draw the Lewis structure of carbon dioxide, it would be AX2. I think we may have seen that one last time or talked about it before. So carbon dioxide is a linear molecule. So I'm going to draw it exactly as a linear molecule. It does have lone pairs on the oxygen that aren't so important for determining polarity. Now what we have in carbon dioxide is we have two polar bonds, right? Carbon-oxygen bonds are polar. So if we go to the periodic table to convince ourselves of that, carbon is here, oxygen is here. Oxygen is significantly more electronegative than carbon. Oxygen is about 3.5 on the electronegativity scale. Carbon is 2.5, so that's a substantial difference. So you have individual bonds are polar. So we have delta minuses on each of the oxygens here. If we want to be quantitatively accurate, we would write this as 2 delta plus because there's two polar bonds to that carbon. Not that that's that important. But point being is that the individual carbon-oxygen bonds are still polar. However, if we think about the directions of these dipoles, remember they point towards the more electronegative atom. We have one dipole that points left to right, and we have an exactly identical dipole that points right to left. And so those two completely cancel each other out. You can almost think about it as a tug of war. You have one oxygen pulling electron density this way, the other oxygen pulling electron density that way towards itself. Those two cancel each other out, and overall the molecule ends up being nonpolar. There is no unequal distribution of charge in this molecule. All right, so this ends up being an example of a nonpolar molecule. Okay. Another one that's not as obvious, but I'll show you, is if we have BF3. So BF3 would give us a trigonal planar molecule, AX3. All right, and again, we have 3 polar bonds now in this molecule. All the BF bonds are very polar. But what we see is that we have one dipole that points in this direction, one that points that way, one that points that way. So basically the two horizontal components of these bottom ones cancel each other out, and the combined vertical components of these two cancel out with this vertically aligned dipole. So again, not as obvious here, but if you guys are, have taken some of your physics courses already, and you can decompose vectors into x and y coordinates, these would also completely cancel each other out. So this would be nonpolar as well. And then one that's even more difficult than this to imagine. This is basically one dimension. This is two dimensions. A three-dimensional example would be carbon tetrafluoride. So that's going to be tetrahedral. Four polar carbon-fluorine bonds, but you have dipoles going towards each of them that end up canceling each other out in total. Now, as I said, though, with the exception of linear molecules, this is kind of hard to picture. You have to think about vectors in 2 dimensions or even 3 dimensions, and it would be really complicated to do that. So there is a pattern that develops, okay? And so what is one thing, if you can notice, what is true about all 3 of these molecules? Can anybody see a commonality that they have about the central atom? Yes. So they are symmetrical, yes. And what is it? And if we think about the AXE notation, what's true about the central atom in all of these? So we notice the central atom, sorry. Exactly. So the central atom in these molecules, none of them have lone pairs. So if we have an AXM molecule where all the X's are identical, or I should say with no lone pair in the central atom, these are all going to be nonpolar. All right, so this one is AX2 with no lone pairs in the central atom. This one is AX3. This one is AX4. So if you went all the way up to AX5 and AX6 with no lone pairs in the central atom, all of the outer atoms have to be the same for this to be true. Those are ones that you can quickly identify as being nonpolar for any of those electron group arrangements. Okay? These are not the only ones that are nonpolar. We'll see some other cases where there are, even if you have lone pairs, they're nonpolar. But no lone pairs in the central atom, identical outer atoms is going to be nonpolar, and that's one that's easy for you to look for in the problems we'll give you, which often asks you to identify whether a molecule is or is not polar. All right, so any questions on that? All right, the next situation we have would be a bunch of examples now where you have polar bonds, but the molecule is polar. So as I said, there's a lot of molecules where you have polar bonds and still net polarity. So this is when the molecule is not perfectly symmetrical. So somebody, when describing the previous molecules, used the word symmetric, which is a good way to think about it. And so when the molecule is not perfectly symmetrical, or symmetric, I guess, those individual bond dipoles will not cancel out, and a net dipole results. Now again, for this, you sometimes have to be able to think in 3 dimensions in a little bit, but an easy example of this would be if you have water. Each of these OH bonds is polar, and water has 2 lone pairs as well, but we don't really think about lone pairs too much when we're talking about polarity. Each of these has a polar bond that points towards oxygen because we have oxygen being more electronegative than hydrogen. Now in this case, though, this is a bent molecule, so the 2 dipoles are going sort of at an angle relative to each other. So these 2 dipoles actually reinforce each other. They don't cancel out. And again, if you want to think about this from the standpoint of vector addition, the 2 horizontal components of these dipoles point towards each other and cancel out, but there's a vertical component that reinforces. And so what you get then in water is a net dipole that goes from the bottom to the top. And again, this is an example of how molecular dipoles don't necessarily reside on individual atoms. You don't have necessarily the positive and negative sides on individual atoms, but you here have a region that's partially positive at the bottom where the hydrogens are, as I've drawn it, and then the oxygen, the top part of the molecule, being the partially negative, and you get that sort of unequal balance, unequal distribution of charge. So these are situations where when the molecule is not perfectly symmetric, a net dipole results. In this case, you have two lone pairs, so as we'll see, most of the structures that have lone pairs in them are polar. I'll give you a full table that shows all the possibilities later on that are helpful to get familiar with, but again, you want to think about what is the molecular geometry, whether the individual bond dipoles do or not cancel out in those situations. And then finally, we do have situations where you can have, out of order here. All right, so you do have situations where even though they are one of those AXM structures and don't have any lone pairs, they can still be polar. So sometimes molecules that have the same shape can have different polarities. So what I want to point out on this slide is that molecules without lone pairs can be polar. Lone pairs on the central atom, I should say. It is possible for them to be polar if they have more than one type of outer atom. All right, because remember, these individual bond dipoles, they have a direction associated with them, where if they're all the same and those directions cancel out, you have no net polarity, but they also have a magnitude associated with them. So we gave the example earlier of carbon tetrafluoride. Let me do a simpler one for this, because these tetrahedral ones are hard to think about. Let's start with, okay, so we started with CO2, right? And as we saw last time, this one is nonpolar because we have two identical bond dipoles that cancel out. But what if we do another molecule that's linear, but we replace one of the oxygens with sulfur? Let's do SCO. All right, same type of structure, linear, AX2. But now what we have is we have a relatively large dipole pointing this way towards carbon and oxygen, but the carbon-sulfur bond is a lot less polar because the electronegativity of sulfur and carbon is more similar. So if we go to the periodic table, we see that carbon-oxygen has sort of this polarity. Sulfur is less electronegative than oxygen. I think it's still a little bit more electronegative than carbon, but it's going to be a smaller dipole for the carbon-sulfur bond. And regardless of whether that detail is appreciated or not, we can understand that this dipole is not going to be the same. So we have a dipole pointing that way, but it's smaller. So if we think about sort of the tug of war between the two sides of the molecule for electrons, there's going to be a stronger dipole towards oxygen than there is towards sulfur, so they no longer cancel each other out. Because in order for them to cancel, they have to be opposite in direction and the same in magnitude. In this case, they're not. They're just opposite in direction. So this one would be polar, and you'd have a net molecular dipole still pointing left to right towards the most electronegative atom. Okay? Or if we go to, we said BF3 was nonpolar. If we go to BF2Cl, you have, again, two large dipoles pointing this way, a comparatively smaller dipole pointing that way, which I'll show with a smaller arrow. And so this also ends up being polar with a dipole that sort of, again, probably points down towards the fluorines, would be the net direction of that dipole towards the more electronegative atoms. So it is possible if the outer atoms are not all the same and they have different electronegativities, you're not going to get those dipoles all canceling each other out like you would if you had three identical atoms bonded to boron or two identical atoms bonded to carbon as we did in the first one. So keep in mind that just because it's AXM and doesn't have any lone pairs, it might still be polar if you have more than one type of atom bonded to the central atom. All right, any questions on that? All right, so then what we'll close with is just one example. No, don't do that, don't do that. Jeez. There we go. All right, so we want to choose the nonpolar molecules from the following. And again, the whole key to all of this is to be able to draw the Lewis structures, at least get a good approximation of it. So we can, we have four to choose from here, and I'm not going to go through all the details of this, but if we started with SO2, we would find that we have 18 valence electrons. And so when we draw this Lewis structure, we start with this. And again, for these types of arguments, whether or not you finish the structure or not, we really should at least put one double bond in there to complete the octet. But however you do it, you're going to end up with one lone pair in the central atom. This is going to be a bent geometry. And any bent molecule, it doesn't matter what atoms are involved, is going to be polar, because in a bent geometry, you're never going to have dipole moments canceling each other out. So this would be bent, so this one would be polar. So if we're looking for the nonpolar molecules, we can cross that one out. And then we're going to not do all of these, but if we go to SF6, what we find is that this one ends up being AX6, so there's no lone pairs on the central atom. And as we said, all of the AXM structures with 0 lone pairs on the central atom, you get an octahedral structure in this case, but all of these would be nonpolar. You have 6 polar bonds, but all of those cancel each other out when you don't have any lone pairs in the central atom. So that one's going to be nonpolar. PCl3 was one of the first ones we did, and as we saw for that one, we got AX3E. So that's going to be our trigonal bipyramidal geometry, and this will be polar as well. All right, because anytime, and then something else, another pattern we'll see that I'll close with on the next slide is that anytime you have one lone pair, it's definitely going to be polar, regardless of what else is in there. So one lone pair is always polar, bent is always polar. There's a couple you can remember that are helpful, and this one would be one that's always polar. So that's going to be so we're looking for nonpolar ones, so we cross that one out. And then finally, PCl5. I think we also did this one last time, so we don't have to necessarily go through all the details again. This came out to just AX5. This geometry is a little bit weird, but still has the same pattern that when we have no lone pairs on the central atom and only one type of atom bonded to it, we're going to get a nonpolar molecule. Don't freeze. All right, so we get AX5 trigonal bipyramidal, but because there's no lone pairs, it does come out to be nonpolar. So that's another nonpolar. So number 2 and 4, choice B, are nonpolar. So this is a typical type of question. We'll ask you to distinguish polar from nonpolar. If we ask you to find the molecule that's least polar, you would first look for ones that are nonpolar, because those have 0 polarity and so on. So any questions on this topic? All right, so to help you summarize this, again, not something that I want you to necessarily memorize, here's a table that relates all of the AXE geometries to whether they're polar or nonpolar. Now again, this only works for all x's being the same on the central atom. So if you have 2 different types of atoms bonded to the central atom, some of this breaks down, as we saw at times. But there's some important trends here. So if you have 0 lone pairs, all of those, as we said, are nonpolar. If you have 1 lone pair, which is this column, all of those are polar. If you have 2 or 3 lone pairs, it's a mix and match of the both. We have to kind of think about the geometry. But anything with 1 lone pair is polar. Anything that's bent is polar. And then there's just a few more here, T-shaped, square, planar, linear, that you have to work through and rationalize whether they're polar or nonpolar. But this table sort of summarizes all the common geometries, and a good portion of the questions we give you will deal with molecules of this type. Central atom, some type of atom bonded around that central atom, and predicting whether it's polar or nonpolar. All right, the next topic we're going to move into now, which I would say conceptually is fairly difficult, if I'm being honest, but the types of questions we're going to ask you about it I don't think are that difficult, and that's going to be dealing with bonding in these covalent molecules. So we haven't really talked yet about how exactly do we share 2 electrons between 2 atoms, or especially if we want to make these larger, more complicated molecules, AX3, AX4, AX5, how exactly are the electrons distributed and shared? And what we should think about is that the individual atoms that make up these molecules, they of course have those electrons are arranged into orbitals. We talked about electron configurations in chapter 2, how all the electrons are arranged into subshells in the ground state. And so then when we bring 2 or more atoms together to form molecules, how do those orbitals change, or how do they interact with each other? So a simple model for explaining chemical bonding is just that we take simple atomic orbitals and we overlap them to form a bond. So if we have hydrogen, which is H2 being the simplest molecule out there, 2 atoms, 2 electrons, remember that each hydrogen atom has 1 electron, and it's going to be located in a 1s orbital. We take a second hydrogen atom, which has 1 electron in a 1s orbital. And then when we combine these together, we get H2. And a simple model for explaining the bond between the 2 hydrogens is that these 2 1s orbitals overlap with each other. Let me try to draw this a little bit better. So you get 2 overlapped 1s orbitals. I'll draw this a little bit bigger so I can show you everything here. So you get 2 spherical orbitals that overlap. Again, the nucleus being at the center of each of these. And then in the region where they overlap, you share the 2 electrons. Now, because they're in the same region, they have to be 1 spin up, 1 spin down. So same sort of Pauli exclusion principle. You have 2 electrons now occupying the same orbital, more or less, and they are 1 spin up, 1 spin down. But this is sort of the first type of bonding model we're described is called valence bond theory. And what this theory says is that you have atomic orbitals involved in the individual atoms. You bring them together, and those atomic orbitals overlap, and the electrons are shared in that overlap region. Now, if we go to a more complicated case like chlorine, we know that the valence electron configuration for chlorine from the periodic table is 3s2, 3p5. And what this valence orbital or valence bond theory sort of suggests to us is that it's going to be unpaired electrons that are shared. So if you have unpaired electrons, they're going to pair up with another unpaired electron and form a bond. So if we look at chlorine, we have filled 3s orbitals, but we have 1 unpaired electron in the p orbitals that we're going to be able to form a bond with. So each chlorine atom is going to have a 3p orbital. As we learned before, these orbitals have this sort of dumbbell or figure 8 shape to them when they're p orbitals. So we have a 3p orbital on 1 chlorine atom that has an electron in it. We have a 3p orbital from another chlorine atom that has an electron in it. And just like we did for hydrogen, we can take those 2 3p orbitals, bring them together, overlap them in the middle, and share the 2 electrons in the region where they overlap. So this is, again, the simplest bonding theory, which just assumes that simple atomic orbitals come together. As we'll see, this is not entirely correct, but it is a good start and a good model for us to base a lot of things off of. But there are some places where this will break down. All right? So we get this sort of overlap situation, 2 3p orbitals overlapping, nuclei at the center of each orbital to make Cl2 with a shared pair of electrons in that region where the 2 orbitals overlap. So this is, again, the basics of valence bond theory, overlapping atomic orbitals, and they don't necessarily have to be 2 of the same type of orbital. So if we have HCl, the hydrogen is going to have its unpaired electron in a 1s orbital. The chlorine, as we saw, is going to have its unpaired electron in a 3p orbital, and those 2 can overlap with each other as well. So we have a 1s from hydrogen with an unpaired electron. We have a 3p orbital from chlorine with an unpaired electron. And these 2 can also come together to make a bond where the 1s orbital from hydrogen overlaps with the 3p orbital from chlorine. So you have a 1s of 3p from HCl, and then a shared pair of electrons in the region where the 2 orbitals overlap with each other. So a lot of different combinations, but for these simple diatomic molecules, or for just thinking about the bonds between 2 different atoms, we can just use atomic orbitals. Those have unpaired electrons in them in these cases. Those 2 orbitals can point at each other and overlap, and then you share the electrons right where those 2 overlap with each other. So that's kind of the simplest picture of what's called valence bond theory. So when we're talking about overlap atomic orbitals, that's referred to as valence bond theory, or VBT. But there's some more complicated situations that arise. So in some cases, what happens is, let's say we have more than 2 atoms bonded together. So if we have linear or trigonal planar or tetrahedral, how do the orbitals work in that situation? So if we go to one example would be a linear molecule. And in this case, what we do is, let's take the example of beryllium chloride, BeCl2. If we look at the central atom, so we know that each chlorine has an unpaired electron that can overlap. But if we look at the central atom beryllium's valence orbital is 2s, and it's a 2s2 configuration. So as I said before, well, if we need to have unpaired electrons to be able to form these bonds overlapping with other orbitals, how does that work for beryllium Cl2? Because the central atom doesn't have any unpaired electrons. And so what we do in these situations is we do what's called hybridization. All right, so again, I'm giving you sort of the physical origin of this. The main thing you're going to have to be able to do at the end of this is be able to predict what the hybridization is for a molecule. And as I'll show you, that's pretty simple to do if you have the correct Lewis structure. But the process, the way that it works is if we want to make a linear molecule with beryllium at the center, it doesn't have any unpaired electrons. So what it does is it takes a 2s orbital and a 2p orbital and it mixes them together. So recall that these orbitals are wave functions, which are mathematical functions. So you basically do a mathematical combination, an addition or a linear combination, I guess, of those two wave functions to make two new orbitals. And because we're mixing a 2s and a 2p, so we're mixing 2s with 2p for this situation, we get orbitals that are labeled as sp hybrids. So they have a combination of s and p in them. And then we get still two unhybridized 2p orbitals. So we only require, in this case, to mix one p orbital with the 2s orbital. That gives us sp hybrids. So we still have the same number of orbitals. We have 4 atomic orbitals here. We hybridize 2 of them to make 2 hybrid orbitals, and we still have 2 unhybridized orbitals as well. And now when we fill the electrons into here, these are going to have each one unpaired electron, because the 2 hybrid orbitals end up at exactly the same energy. They have these 2 electrons, and the 2 electrons, because of Hund's rule, arrange themselves like this. So the energy of this sp orbital is between that of s and p, and this energy is going to be unperturbed, and these aren't actually going to be used in the bonding at all. All right, so then finally what we do is we take these 2 unpaired electrons and we're going to overlap them with the unpaired electron in the chlorine 3p. So in this case, we're not using pure atomic orbitals to make the bonds. We're taking 2 of the atomic orbitals on the central atom, hybridizing them, and then it's those orbitals that overlap. And these are oriented in exactly the right direction to give the molecular geometry. So we would predict that this is a linear geometry AX2, and these 2 sp hybrids are basically pointing at 180 degrees from each other, and they overlap with the chlorines on either side to make that linear molecule. So that's the process by which hybridization happens. We can look at a slightly more complicated example. So if we have BF3, we would predict that this is an AX3 geometry. And anytime we have AX3 as the electron group arrangement, we're going to get what's called sp2 hybridization. So let's see how that works. The geometry associated with this is trigonal planar. And I think this is the situation too, this picture here, which hopefully will help you understand why do we have to hybridize to begin with, or what's one of the reasons for doing that. And because if you think about it, if we were to try to use atomic orbitals for this, in boron, which is our central atom, we have a 2s and a 2p orbital as valence orbitals. For boron, the 2s is filled. For 2p, we have 1 electron in there. Now again, we have the same problem. If we're going to form 3 bonds to make BF3, we only have 1 unpaired electron to do that, so that situation arises. But we also have a pretty clear geometry problem here. So we said this is a trigonal planar geometry, which means we have 120 degree angles. But if we were to just use pure atomic orbitals, the shape of a 2s orbital is spherical, and how are the 3 2p orbitals arranged relative to each other? What's their angle between them? And we have px, py, and pz, so what's the angle between all of those? What's the angle between the x and y coordinates? 90 degrees. So we have our if we were just use pure atomic orbitals, we couldn't make 120 degree bond angles because the p orbitals on the central atom will be pointed 90 degrees from each other, there's no way to get 120-degree bond angles or a triangular geometry. So this is another reason why we hybridize, is to arrange the orbitals in the correct orientation to make these predicted shapes that we've been talking about. So in the case of BF3, we're going to hybridize, again, orbitals only on the central atom, as how we think about this. So we take this 2s orbital and we hybridize it with the 2p again, but this time we're going to use 2 of the 2p orbitals. So we get a set of 3 orbitals now that we would label as sp2 because they came from 1s and 2p orbitals mixed together. And they form a set of 3 other identical orbitals that are in between s and p. They have character from both. And these sp2 orbitals have 3 unpaired electrons now. So all 3 valence electrons end up in the sp2 orbitals. They overlap with the valence electrons from fluorine to make the bonds. And that's where you form your 3 bonds. And again, in this situation, we still have an empty 2p orbital. Now, these 2p orbitals will be important at times, so they're unhybridized and they don't contribute to the bonding in this picture, but we'll see where they come into play a little bit later on. So that's an example of sp2 hybridization. And then finally, the last one I'll do, there's more than this, but we just don't want to repeat ourselves over and over again, is sp3. And this is, again, a situation where if we were to try to just use atomic orbitals, we would have a problem with geometry because sp3 hybridization is going to be associated with the tetrahedral geometry, or more specifically the tetrahedral electron group arrangement. Tetrahedral, as we said, is 109.5 degree bond angles. We just got done describing how the atomic p orbitals are oriented at 90 degrees with respect to each other. So again, not the right angles to make a tetrahedral geometry. And so if we have methane, CH4, we have carbon, which has 2s and 2p valence orbitals, 2s2, 2p2. Again, in the unhybridized form, there's only 2 unpaired electrons. You can really only form 2 bonds with this. So we hybridize all of these orbitals. And this time we want to form 4 identical bonds. So we need to hybridize 4 of the orbitals. We need to hybridize the 2s and all 3 2p's with each other. And this time we get an identical set of orbitals that we abbreviate as sp3 because they come from 1s and 3p orbitals. 4 identical orbitals, 4 valence electrons that are now all unpaired, and that allows you to form 4 bonds. So you have 4 orbitals, all equal energy, and all able to form bonds that are tetrahedrally arranged. So that's kind of the orbital picture of how hybridization happens. Again, there's a lot more math behind it that we're not going into of how these orbital wave functions combine with each other to make new wave functions that have different properties from the original. But hopefully this gives you an idea of what the process is. It's taking atomic orbitals in the central atom and blending them together to make new orbitals that are now involved in forming the bond. Now, as I said, though, what we're really going to have you guys be doing in here not so much is thinking about these pictures that I drew and sort of just predicting the hybridization of a molecule. And this ends up being very easy to do. So all you need to know to be able to predict hybridization is the steric number, which again we said is the total number of electron groups in the molecule. Okay? So all you need to know is the total number of electron groups, which is that in the AXE notation, m plus n, the number of total electron groups around the central atom. If you know that number, which of course requires you to have a reasonably correct Lewis structure, once you know that number, you can predict the hybridization of any atom in any molecule. Okay? So, and this is talking about specifically the central atom. So we're predicting here the hybridization of the central atom in cases of the types of molecules we're working with. Okay? So if our steric number is 2, here's the valence orbitals that are available in the types of molecules we're looking with. Again, we have an s orbital, 3 p orbitals, and then in some cases, as we'll see, the d orbitals even get involved. We have a possibility of 5 of those getting involved. So these are the valence orbitals, atomic orbitals available. If we're going to have a steric number of 2, we need to hybridize 2 orbitals. So we take the first 2 of these, 1s and 1p, and that becomes sp hybridization. And the geometry associated with that, of course, or the electron group arrangement more specifically, is linear. So we'd have sp hybridization. If the steric number is 3, we have to hybridize the first 3 orbitals, 1s and now 2p's. So that becomes sp2, and that's trigonal planar arrangement. Steric number of 4, either AX4, AX3E, AX2E2, we need to hybridize 4 orbitals. So we take the S and all 3 p orbitals, and that gives us sp3. Tetrahedral would be the arrangement of those orbitals. Now finally, these last ones here, this is where I hate to admit that we lied to you a little bit, but if we go beyond a steric number of 4, we can't just use S and P orbitals anymore if we're talking about the hybridization model, because we only have 4 of those orbitals available. So the way that it's conventionally justified is, well, if we have a steric number of 5, let's use 5 orbitals, and let's start using the d orbitals and mixing those in. And that gives us a total of 5 atomic orbitals that we can mix together to make 5 hybrid orbitals. We call this sp3d, or sometimes dsp3. We put those in different orders, but that's what we call it. And this would be the hybridization associated with the trigonobipyramidal geometry. Now this is a model that, again, it works pretty well for predicting the geometry, and if you actually do the math and hybridize an s orbital, 3p orbitals, and a d orbital, you get a set of orbitals that are arranged in a trigonobipyramidal fashion. It turns out more detailed analysis later on sort of revealed to people that d orbitals are not really that involved in bonding when you have main group p elements. So when you're talking about central atoms like sulfur, chlorine, or iodine, things in the p block, even though you sometimes predict sp3d hybridization, the reality is the d orbitals don't really participate actually in the bonds. So it's kind of a lie that we tell you, but it's an easy way of justifying or rationalizing these geometries. And if we ask you to predict the hybridization of anything that has 5 electron groups, just say sp3d and sort of ignore the fact that you're lying to yourself and that I've lied to you. All right, so that's just a little aside about whether that's really true or not, but it is a good way of at least rationalizing things in terms of this valence bond model that we're talking about today. And then finally, the last one is 6 electron groups. We hybridize 6 orbitals, so we take 1 s, 3 p's, 2 d's, a total of 6 orbitals gives us sp3d2, or sometimes written as d2sp3. And that hybridization results in an octahedral arrangement of those valence orbitals, okay? So this is how we predict hybridization. You just need to know the steric number, and from that directly falls out what the hybridization would be. All right, so any questions on that in abstract? All right, so let's go through a couple examples. Let's do COCl2 and predict the hybridization of the central atom. All right, so what we have in this molecule, again, is we have to get a Lewis structure. So we have 1 carbon, 1 oxygen, 2 chlorine. So carbon is group 4, so that contributes 4 valence electrons. Oxygen is group 6, that contributes 6. Chlorine is group 7. We have 1 oxygen. Only one. Whoops. Got ahead of myself. And then 2 chlorines, which each contribute 7 valence electrons. So this molecule should have 24 valence electrons. When we draw the structure out, we get this. We start out with putting lone pairs on the outer atoms. We've completed 3 octets. We've used up all 24, so we don't have any left for the central atom. Our central atom does have a deficiency. It only has 6 valence electrons, so to fix that, we draw a double bond to oxygen. And that would be our final structure. But again, whether we did that last double bond or not, we will predict that this is an AX3 structure. It's a central atom, 3 atoms bonded to the central atom. And as we said, all we care about for predicting hybridization is steric number. So if we have s and 3p orbitals available, we never involve d orbitals for carbon and things in the second row. Remember, that's only going to come into play if we have more than 4 electron groups or more than 8 electrons. But in this case, we just need 3 electron groups, so we hybridize an s with 2p orbitals, and that gives us sp2 hybridization. All right, so again, once you've drawn the Lewis structure, or at least a close approximation of it, even if you forget double bonds and things, as long as you know the total number of electron groups in the central atom, predicting hybridization is very straightforward. All right. Now, we will also give you examples like this, where we will want you to complete the Lewis structure and predict the hybridization of all the carbon atoms in the following molecule. Now we've come across some structures like this already in chapter 3, some more complicated Lewis structures that have this sort of chains of carbon atoms. And again, the pattern we want to follow for this for completing the Lewis structure is we have carbon, oxygen, in this case hydrogen in this structure. Carbon is going to tend to have 4 bonds exactly, and no lone pairs. Oxygen, 2 of each. Two bonds and 2 lone pairs. Hydrogen, of course, just 1 bond. We don't have nitrogen in this structure, but if we did, it would be 3 bonds and 1 lone pair. So with the exception of hydrogen, all of these atoms, carbon, oxygen, nitrogen, they want to have complete octets, but they do it in different ways to achieve 0 formal charge. So that's the pattern we want to follow here. So if we want to complete this Lewis structure, we see that this first carbon already has 4 bonds. The second carbon here, though, only has 3 bonds, as does the carbon next to it. So if these 2 carbons have 3 bonds, we can fix that by drawing a double bond between them. So we can make a double bond there. Now both of these carbons have 4 bonds. This carbon has 4 bonds, so it's happy. But if we get to this one here, we have 3 bonds for that carbon, only 1 bond for this oxygen. Carbon wants to have 4 bonds, oxygen wants to have 2, so we fix that by drawing a double bond there. And this would also have 2 lone pairs. And then finally, when we get to these last 2 here, what we see is that we have this carbon only has 2 bonds, so does this carbon. We can't draw any more this way because we've already put 4 bonds onto that carbon. So we draw 2 more bonds to that carbon. That gives us 4 bonds for each of these as well. So again, a little bit of a puzzle to put it together, but work through all the atoms and try to make sure that each carbon has 4 bonds, and if you have oxygen, it would have 2 bonds and 2 lone pairs. So that's the final structure we get, and then we just have to go through and predict hybridization. So this carbon here has 4 electron groups around it, so that makes it sp3, a total of 4 orbitals that get hybridized. These 2 are going to be the same as each other, so this carbon has 3 electron groups bonded to it. This carbon also has 3 bonds, 3 things bonded to it, so it's going to be sp2 for both of those. This carbon here has 4 things bonded to it, so it's sp3. This one has 1, 2, 3 electron groups attached to it. Remember, we don't care if it's a single or double bond, it's just whether it's bonded or not. And so this one gives us sp2. And then we have 2 carbons here that each have 2 electron groups. This one's bonded to this carbon and that carbon. This one's bonded to the carbon and the hydrogen. 2 electron groups, we hybridize 2 orbitals and get sp. So this molecule has all 3 possible hybridizations for carbon, sp, sp2, and sp3. And again, it just comes from counting how many things are bonded to that carbon, how many total electron groups does it have. All right, any questions on this? Yeah. So that's basically a pattern that evolves from doing Lewis structures. If you have a neutral molecule, organic molecules as these are, carbon, oxygen, nitrogen, they want to have, this is 1 lone pair. Carbon, oxygen, and nitrogen, they all want to have a total of 8 electrons around them. Each bond is a pair, each lone pair is a pair. But you also want to minimize formal charges. So the way that you do that with carbon is to give it 4 bonds. That gives it 8 total electrons around it, 2 from each bond, but then also no formal charges as well. So this is kind of the pattern that you'll see for a lot of these types of Lewis structures, especially organic molecules like this that have these long chains of carbon with other oxygens and hydrogens and things thrown in. So it's a good pattern to know, because otherwise you have to go through and count the total number of electrons and figure out which ones have incomplete octet. Do they need lone pairs? Do they not? But if you follow these patterns, I think you can do it a lot faster. Anything else? Okay. Yeah, sorry. I mean, I wouldn't say always, because we did one in the exam review, carbon monoxide, where it had 3 bonds. But typically speaking, especially in organic molecules like this, 2 bonds, 2 lone pairs. That could be either a double bond or 2 single bonds, any combination of 2 bonds. And that's very often what you see for oxygen. All right? Any other questions? All right, now the next thing we're going to get to is the types of bonds that form. So not all covalent bonds are the same as each other. I feel like I'm missing something here. All right, well, I think I'm going to have to wing it because I think I forgot some of my notes. It's just been that kind of a week. Alright, this will be fun. I just have to do this off the top of my head. So if this sucks, I'm sorry. Alright, so anyway, we have two types of bonds. We have what are called sigma and pi. Alright, so in a sigma bond, you're going to have what I should say shared electron density. So remember that in a bond, you have two atoms that are sharing electrons. You have orbitals that are overlapping to make those bonds. And so you're going to have some sort of shared electron density that resides in between the two atoms that are bonded together. So the electron density is in between the nuclei along the direction of the bond. All right, and so when you have sigma bonds, then there's basically the types of orbitals that are involved. So what overlaps to make sigma bonds? You're going to have either so hybrid orbitals are very often involved in making sigma bonds. One thing I should point out is that hybrid orbitals, they only make sigma bonds. We're going to talk about one other type of bond as well. And so if you have hybrid orbitals, those orbitals will only make sigma bonds. Sometimes hybrid orbitals also include the lone pairs in them, or usually they do, but they don't make the other type of bond. They only make sigma bonds. And sometimes you can have regular atomic orbitals. All right. So if you want to draw a picture of a sigma orbital, these are, again, situations where the two orbitals that are overlapping are pointing right at each other along the direction of the bond. So if you have, let's see, what would be a good one to do for this? If we do carbon dioxide, CO2, that's sp hybridized. And so the sigma bonds are going to be carbon, which has a sp orbital, and it's going to overlap with oxygen, which has either a hybrid orbital or atomic orbital. And again, these are that same type of picture we showed before, where the bonds overlap, the orbitals overlap right in between the two, and they're going to be along the direction of the bond. So in this carbon-oxygen bond, that's the direction of the bond, the vector between carbon and oxygen, and the shared electron density is right in between those two for a sigma bond. Okay? And then we'd have one in the other direction as well, obviously, for making CO2. Which is, again, another sigma bond. So you have one sigma bond going in each direction. But then the other type of bond that we have are pi bonds. Okay? So the definition of a pi bond is you have the shared electron density is above and below the bond vector. All right? So you have shared electron density above and below. That means it's no longer along the direction of the bond. It's actually above and below those two. And so the types of orbitals that are involved, these are the types of bonds that are formed when you have unhybridized p orbitals. So the only type of, at least in the general chemistry sense, it's more complicated than this later on in chemistry, but in this course, we just have to think about unhybridized p orbitals as being involved in forming pi bonds. All right, so hybrid orbitals are never involved in forming pi bonds, only going to be unhybridized p orbitals. And so what that means then is if you have two p orbitals, so if we have a CO double bond, let's just do one CO double bond, it's hard to draw both of these together, you would have carbon and oxygen, you'd have a sigma bond in between them, so you still have the sigma bond, but then the second bond, which is part of the double bond, is going to be a pi bond. And in that case, what you get is a p orbital on each atom, unhybridized p orbital. And again, this is where it's also helpful to put in the phasing of the orbitals. So you have, in a p orbital, you have a positive lobe and a negative lobe, which we indicate with different colors here. And the lobes that are the same phase are going to line up with each other. and they're going to form a pi bond where you have basically shared electron, a little bit hard to draw, but you have shared electron density sort of above and below the plane where these p orbitals overlap. All right, so you get this overlap above and below, and that makes your pi bond. All right, the sigma bond being along the direction of the bond, the pi bond being above and below. And then if we wanted to do CO2, this is going to be hard to draw, but essentially in CO2 we have sp hybridization. So that means we have two unhybridized p orbitals. And so what that ends up with is we have, again, our sigma bonds, which I'm not going to draw in their full detail, which involve the sp orbitals. And then we have pi bonds that are going to be above and below the plane. So we have one that's in this direction. Now this one, the second one's going to be hard to draw because if you remember, if we have two unhybridized p orbitals that are both going to be perpendicular to the sp orbital, the other one is rotated 90 degrees from this one. So you're going to have another p orbital that, as I'm going to try to draw, sort of comes out of the page and into the page. And it's going to have this option is going to have a p orbital that faces the same direction, and you're going to get overlap along those. So if you have CO2, you have two pi bonds, one in each direction, but they're rotated relative to each other. But the key point of all that is that the pi bond forms when you have overlap above and below the direction of the bond. And that's what we call pi bond. It's going to be p orbitals that are side by side relative to each other, and they're sharing their electron density above and below the bond. That's the difference there. Okay? All right, any questions on that concept? Again, the picture is a little bit complicated, but we can clarify some things. All right, well, I will cry myself to sleep tonight as I think about this question. I know, yeah, so I would imagine your book has better pictures of it than this. Essentially, all right, I'll get an answer out eventually once I finish wiping the tears off my eyes. So eventually, what we want to think about is you have your hybrid orbitals are going to be arranged in the geometry that you would predict for the molecule. So if we have a linear molecule, we have two hybrid orbitals that face out in that 180 degrees from each other. And if we have a trigonal planar molecule, we have three hybrid orbitals that are in a trigonal plane. And then within that, you're going to have, if you have unhybridized p orbitals, those are going to be perpendicular to that, and those are going to overlap. So hopefully this picture at least makes sense. Two p orbitals overlapping with each other. P orbitals have that figure 8 shape, and they can go above and below the plane of the bond or the direction of the bond and overlap that way. But I do think if you want to find better pictures than what I've drawn, I would imagine the textbook has them, although I haven't looked at that chapter in a while. But think about sigma orbitals being a head-to-head overlap. So basically, coming back to the very beginning of what we talked about in this section, these first bonds that I drew where I showed two orbitals kind of coming together head-to-head, that's a sigma bond. Okay? Two orbitals coming straight at each other, sharing electrons right in between those. That's sigma bond. The other type of bond is a pi bond, and that's where you have, it has to be p orbitals. Those are the only types of orbitals that can form these types of bonds, at least in our types of molecules we work with. And the p orbitals are side to side relative to each other, sort of facing the same direction on each atom, and they overlap above and below. So that's kind of the picture we want to think about. This picture is more complicated, as I said, because you have one set of p orbitals that would be in the plane of the page. That's this one on the right side here. The other set of p orbitals is going to be rotated 90 degrees to that. It's going to look the same, but it's rotated 90 degrees. And as bad as I am at drawing in 2 dimensions, I'm even worse in 3, so that's why that picture is a little bit confusing. But an individual pi bond looks like this, overlap above and below. The more important thing for you guys is going to be to predict how many of each there are. So again, the pictures are potentially helpful for understanding these types of bonds. You guys are going to get problems on your homework assignments and tests where it says, okay, in this molecule, or for this central atom, or whatever the reference point is, how many sigma and pi bonds does it have? So again, you have to draw a Lewis structure. In this case, figuring out double bonds and triple bonds is fairly important because that actually does play in when we're talking about sigma and pi bonds. And then you just have to say there's this many sigma and this many pi bonds. All right, so if we look at valence bond theory, this is, again, the theory that we're talking about today with overlap of atomic orbitals or hybrid orbitals. If you have a single bond, it's going to be a sigma bond by this theory, okay? Okay? So all sigma bonds are sigma bonds. So the bond order is 1, it's a sigma bond, and that's all you have to think about. That's never going to be a pi bond, at least based on this simpler theory, valence bond theory. If we go to multiple bonds now, so double bonds and triple bonds, you're going to have one sigma bond as part of that multiple bond. The rest will be pi. All right, so if we have a double bond, that's 1 sigma and 1 pi. Total of 2 bonds, 1 is sigma, 1 is pi. And then if we have a triple bond, still 1 sigma bond, and now we have to have 2 pi bonds to make the total of 3, and that's as high as we go, is the triple bond, okay? So just for being able to predict what kind of bonds it is, you have to have a Lewis structure that shows correctly the bond orders between all the atoms. Otherwise, you cannot predict whether it's a sigma. Now, every bond will involve a sigma bond, but if you want to know how many pi bonds there are especially, you need to know is it a double bond, is it a triple bond, and so on. All right, so that's how we make predictions about it. And so then if we go back to this molecule that we drew earlier, and we want to know how many sigma and pi bonds are in here, we just look at the structure. This is the complete structure that we already did before, so we don't have to fill it in with any more double bonds or triple bonds. They're already there. And we just have to figure out, which ones are sigma and pi by looking at that pattern that I just introduced. So if we have this carbon here, all 4 of its bonds are single bonds, so it's going to make 4 sigma bonds. And again, relating it to hybridization, we earlier predicted that this carbon is sp3 hybridized. It has 4 hybrid orbitals. Those hybrid orbitals can only make sigma bonds. They can't make pi bonds, so you get 4 sigma bonds for this carbon. These next 2 here, though, as we saw, were sp3 hybridized. And so they each have this sigma bond to the carbon before it for this one here, but then we have all of the CH bonds are going to be sigma, but then this carbon-carbon double bond is going to have a sigma bond and 1 pi bond. So a double bond is 1 of each, sigma and pi. And the way that works, again, is we said that these carbons are sp2 hybridized. So we don't need to think about this necessarily, but just sort of relate it back to the last question we did on this molecule. So these are sp2 hybridized carbons. This one's sp3. In sp2 hybridization, you have 3 hybrid orbitals. Those 3 are involved in making the 3 sigma bonds that this carbon has. And then the unhybridized p orbital that's left over for sp2 hybridization, you have 1 unhybridized 2p orbital. Those are going to overlap on each of these to make the pi bond. So it's for each carbon, it's going to be 2 sigmas and 1 pi. So if we go to this now in this direction, we have another sigma bond here between these 2. So both of these sp2 hybridized carbons are going to have 3 sigmas and 1 pi. 3 sigmas and 1 pi. And it's the unhybridized p orbitals that are going to overlap to form the pi bonds. The hybrid orbitals are going to be involved in forming the sigma bonds. All right, if we get to this next one here, this carbon is also sp3 hybridized, and any sp3 hybridized is going to have only sigma bonds. All right. And then finally, we have this carbon here, sp2 as we saw. It has 2 sigma bonds, which are the single bonds. It has a double bond that's going to be sigma and pi. So same pattern. sp2 hybridization gives you 3 sigma bonds, which are the 3 sp2 orbitals overlapping with other orbitals. And then you have a pi bond, which is going to be an unhybridized p orbital on carbon, unhybridized p orbital on oxygen, overlapping side to side to make a pi bond. And then finally, these last 2 here are sp hybridized. So we have 2 hybrid orbitals, which means we can make a total of 2 sigma bonds. We have 1 sigma bond here, and then we have a triple bond that's going to be sigma and 2 pi's. And then we have this last sigma bond here. Any single bond, any bond involving hydrogen is going to be sigma. Okay? So if we count this up, if I can count is better than I can draw, as we've established. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Did I miss any? Sigmas? You guys are going to rail me if I get that wrong, so let me try it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now I got 14. All right, it's 15. 15 sigma bonds, and then the pi bonds, we have 1 here, and 2 there, so a total of 4. All right, so again, larger structures, we can do the same thing. It comes down to steric number, being able to predict hybridization, and then number of single and double bonds allows us to predict whether they're sigma or pi. All right, so we will go on to the last part of chapter 4 next time, which is a slightly more complex bonding theory, but a more accurate one that we're going to apply to some very simple diatomic molecules. So I'll see you guys on Wednesday.